Non-destructive testing relies heavily on active probes. We use ultrasound to inspect concrete and ground-penetrating radar to evaluate shallow geology, bouncing signals of hidden structures to map their interiors. But these human-generated methods have severe physical limits. When forced into highly dense, heavily fractured, or highly conductive media, acoustic and electromagnetic signals quickly lose their cohesion. They attenuate, fade, or scatter entirely before reaching the necessary depth. This creates a significant blind spot when we need to evaluate massive, hazardous, or completely enclosed structures where drilling is impossible, and placing a standard X-ray machine on either side is geographically absurd. Commercial nuclear reactor containment vessels represent the absolute extreme of this problem. They are heavily shielded, opaque, and introduce severe biological hazards, making continuous internal monitoring exceptionally difficult. To bypass the limits of acoustic and traditional radiological probes, the scientific community uses a completely passive, naturally occurring alternative, the cosmic ray muon. Muons are elementary particles raining down on the Earth from the upper atmosphere. Falling evenly at a rate of roughly 1 per square centimeter per minute, they carry massive amounts of kinetic energy, generating no biological hazards and requiring no artificial power source. By tracking exactly how these particles interact with dense material as they fall, we can translate background atmospheric radiation into highly precise three-dimensional structural data. The process begins 15 kilometers above the surface. Primary cosmic rays, mostly high-energy protons accelerated by supernovae, collide violently with atmospheric oxygen and nitrogen nuclei. These extreme inelastic collisions trigger massive hadronic cascades. The energy creates a shower of unstable secondary particles, primarily charged pions and kaons. Being highly unstable, they decay almost instantly via the weak nuclear force into neutrinos and our target particle, the muon. Under the standard model of particle physics, the muon is a lepton. It shares the exact negative charge and half-integer spin of an electron, but it carries approximately 207 times more mass. This immense mass allows it to penetrate solid matter, but it introduces a severe kinematic paradox. In its own rest frame, a muon lives for just 2.2 microseconds before decaying into an electron. This chart isolates the paradox. Classically, a 2.2 microsecond lifespan restricts a muon to 660 meters, yet the crust is 15 kilometers away. It bridges this gap through special relativity. Extreme kinetic energy triggers time dilation, stretching its perceived lifespan to reach the ground. If relativistic time dilation did not extend their lifespan, these penetrating probes would disintegrate in the upper atmosphere, and muography would be impossible. Once a muon hits solid matter, its sheer mass dictates how it moves. Because it is 207 times heavier than an electron, it mostly ignores the strong nuclear force and avoids the severe braking radiation that stops lighter particles. Instead, its interaction with the target medium relies almost entirely on the electromagnetic force, resulting in two distinct measurable phenomena. The first is ionization energy loss. Plunging through an object, the muon collides inelastically with atomic electrons. Every collision strips away kinetic energy. The rate of this energy drain scales directly with electron density. Pass through enough dense matter, and the muon slows until it is entirely absorbed. The second physical phenomenon is multiple Coulomb scattering. While the muon loses energy to the electrons, its negative charge interacts elastically with positively charged atomic nuclei. These rapid-fire repulsions statistically accumulate, resulting in a measurable angular deflection of the muon's overall path. By recording exactly how much energy is stripped away, or precisely calculating the angle of deflection, researchers map the density and composition of the macroscopic structures the muons pass through. Measuring the total ionization energy lost gives us absorption muography. This method involves placing flat detector planes on a single side of the target, usually underneath, to count the total number of surviving muons. Because we know the baseline rate of cosmic muons arriving from the sky, we simply measure the attenuation. A massive rock absorbs most particles, but a hidden void allows a distinctly higher relative flux to hit the detector below it. Operating from a single vantage point makes this the only option for targets too large to bracket with sensors. Because of this single-sided geometry, absorption muography scales massively. It's deployed deep underground, positioned on active volcanoes, and used to discover hidden chambers inside Egyptian pyramids. While this modality acts essentially as a giant shadow map, its single-point perspective means it sacrifices precise spatial resolution in exchange for sheer operational scale. To recover that high-resolution data, researchers use muon scattering tomography. Instead of just counting surviving particles, this approach tracks the precise trajectory of a single muon before it enters and after it exits. This introduces a strict geometric constraint. The target volume must be completely physically bounded by detector arrays, one suspended above and one below. By calculating the vector difference between arrays, the system isolates the deflection angle caused by multiple Coulomb scattering. The degree of scattering scales aggressively with atomic number. Heavy, high-Z elements deflect muons at sharper angles, turning the array into an exact elemental discriminator. This makes scattering tomography invaluable for cargo security and nuclear forensics. It can detect a dense core of shielded uranium, concealed perfectly within regular commercial goods. It is physically restricted to objects small enough to fit between the sensor arrays, but it delivers true three-dimensional spatial resolution and precise atomic identification. Capturing this data demands rigorous hardware. Because the muon flux is naturally diffuse, detectors require massive surface areas, flawless long-term operational stability, and millimeter-scale spatial resolution. Early particle physicists used track detectors, like cloud chambers, relying on supersaturated vapors to force the ionizing particle to leave a visible condensation trail. These trails had to be photographed and manually measured. While excellent for lab discoveries, relying on manual math is entirely unscalable for modern industrial scanning. The earliest signal detectors were just as inadequate. They operated by ionizing pressurized gas to create an electrical pulse, but the voltage avalanche saturated the tube. Standard Geiger-Müller counters register that a particle hit, but they cannot distinguish a muon from background gamma radiation, nor can they plot a precise directional coordinate. Modern muography relies instead on massive arrays of drift tubes, or tightly packed grids of synthetic solid-state scintillators. When a muon hits a scintillator, the plastic emits a flash of fluorescent photons. A silicon photomultiplier instantly amplifies that light into an electrical pulse. Coupling fast scintillators with high-speed optoelectronics allows researchers to record millions of chaotic atmospheric impacts and instantly digitize them into a clean, millimeter-accurate coordinate grid. Raw coordinate grids and trajectory angles are functionally useless without algorithmic processing. To build a physical map, the digitized arrays are fed through advanced machine learning reconstructions. The POCA algorithm traces the incoming and outgoing scattered vectors to calculate their precise geometric intersection, dropping a voxel point into a 3D grid. As millions of tracks are processed, these points accumulate, translating deflection angles into a high-contrast structural heat map. The software must aggressively filter this data, mathematically correcting for atmospheric temperature shifts that alter the background flux, and adjusting for the geomagnetic field, which naturally bends cosmic rays and creates an east-west trajectory asymmetry. The entire pipeline is a triumph of applied particle physics. It begins with uncontrollable cosmic radiation, 15 kilometers in the air, navigates the kinematic paradox of relativity, and culminates in high-resolution diagnostics deep underground. By utilizing a purely natural flux, muography eliminates the biological hazards of standard radiography. It removes the strict regulatory constraints of active nuclear material and requires no massive external power supplies. A 4 giga-electron-volt muon slices cleanly through heavily shielded vaults and kilometers of dense rock, ignoring the severe limitations that scatter acoustic waves and block radar. Cosmic ray muography bypasses the physical limits of traditional testing entirely. By tracking exactly how the universe's own background radiation interacts with matter, we can map the strict internal geometry of stone and steel entirely from the outside.